Okay, so let us continue our morning session with Larisa Jonke, who will tell us about Hopf and Lie infinity algebras. Please.
Thank you, and thanks the organizer for this kind invitation and organizing for me first conference after 1 year in person, which has been a real pleasure to attend. So let's start with some general motivation. This workshop is named Workshop on Quantum Geometry, Field Theory and Gravity, and I assume that there are different views what is really quantum geometry. So one possible definition, according to Wikipedia, is that we have a set of mathematical concepts generalizing the concepts of geometry necessary to describe physical phenomena at distant scale comparable to Planck's length. However, I think that for our meeting, the community we are here, it's in a sense not broad enough for my taste. So I sort of rephrase it in a sense that it's a set of mathematical concepts necessary to describe and understand quantization of field theory and gravity. So in this talk, I want to argue that one important element of this set of mathematical concepts is Lie infinity algebra. And as a sort of starting point for this research, in physics, we always start from important work of Barton Zwiebach on open and closed string field theories, where he recognized this amazing structure of higher structure of homotopy Lie algebras. For the audience here, I think most of you know what are these algebras. However, even if you don't know it, I'm sure you met it, you just didn't know that it has this name. And some instances where you have seen it here in this community is definitely in field of quantization. First of all, you've seen it as a structure of basically geometric structure underlying BV formalism. Also, you have seen it and it's been used by Konstantinovich in the formation quantization in order to prove the formality theorem. He used the concept of L infinity quasi-isomorphisms. You also see it in different instances in these advances, modern advances in geometry. In particular, I have in mind the graded geometry here, where one can say that L infinity algebra actually corresponds to Q manifolds. If you have additional structure of stochasticity or integral, then it corresponds to QP manifolds locally, very locally. In all the talk, I'm doing stuff locally. And it's also been used in this sort of string-inspired generalized geometry to describe the generalized geometry of current algebroid, double field theory algebroids. The talk you heard from Satoshi, just one before me, handled these, and exceptional algebroids, as they're known. And also for this community, we have instances of this structure, L infinity structure, appearing in certain ways to describe field theory and gravity, in particular non-commutative, maybe even non-associative field theories and gravities. The standard example, which has been mentioned by Vlad, and he was also working on this, is that you can use L infinity structure to somehow construct, bootstrap, consistent non-commutative gauge theory, starting from just given kinematical data or starting from your symmetry. You can bootstrap higher consistently gauge invariant higher interactions. In part of this work, they also recognize that Cyberwit and map, which we used a lot in non-commutative deformation of field theory, can be understood, of course, as L infinity quasi-isomorphism. Another interesting development has been, and partially my motivation to look at these things is the recent series of paper by Maria Dimitrijević-Ćirić, Richard Szabo, Voja Radovanović, and Gregory Yotopoulos on introducing concept of braided L-infinity algebra using drift twist. And these talks we could hear if you were here or following online in the Humboldt College by Richard and by Maria on the previous workshop. And also, as we heard yesterday in the two nice talks by Stefano and Carlo, this structure also appeared in the hairspin theories, which unfolded formalism of hairspin theories in gravity basically also is described by L-infinity algebra. So, for this talk, I want to argue that L-infinity algebra could be also understood as a Hopf algebra with additional structure of co-differential. And to do this, I will say just a few words about Hopf algebra. Just to remind you, I think most of you know what is Hopf algebra. And then I will give two formulations of L-infinity algebra just to see the structure appearing. And then I would like to use this idea that L-infinity is Hopf to twist L-infinity algebra using Drimfeld twist. Okay, Hopf algebra basically is just the algebra that admits antipode. So you have algebra structure with multiplication and unit, and if you can define co-multiplication and co-unit, so co-algebra structure with certain properties satisfied, you have the algebra. The non-trivial ingredient in this is that some B algebras admit antipodes that satisfies this relation, and then they form a Hopf algebra. If they have antipode is unique. Okay, the standard example of the Hopf algebra and the one it's underlying my talk is the tensor algebra, which can be full tensor algebra or symmetric or exterior, the same apply. So in tensor algebra, we have unit and multiplication, and this is co-algebra structure. So you have co-product, you have unit, and you have antipode on vector space V, and this just extends to the whole tensor algebra as written here. Just for the notational sake, this summation over sigma, it's summation over shuffles, which are ordered, and they are called sometimes unshuffled. So first bracket, the shuffles, these permutations are ordered, and in second bracket, the permutations are ordered, and we use the convention that empty product, empty slot means unit, means your field over which you have your tensor algebra. Okay, so just a reminder, it was just a reminder of Hopf algebra. Now I want to tell you something about L-infinity algebra. Basically, in algebraic formulation, this is just extension of a Lie algebra. In the Lie algebra, we have anti-symmetric Lie bracket that satisfies Jacobi identity. If the Jacobi identity is not satisfied, you might be lucky enough that this obstruction for Jacobi identity is controlled by something you can define as being higher bracket, as a 3 bracket, and then you check the next level Jacobi identity for this higher bracket until the structure closes. It can be terminated at finite steps, so you would have like some Lie n algebras, or it can instead to infinity. So basically you have all this set of which are known as homotopy Jacobi identities. So, and this is the algebraic formulation, and in this formulation, an Lie infinity algebra is just a graded vector space with a collection of graded, totally antisymmetric multilinear maps of certain degree 2 minus 1, which satisfy this higher Jacobi identity. Again, we have this summation over shuffles, unshuffle. These are some signs. In particular, this is causal sign since we are on a graded vector spaces element, homogeneous element of each space will have degree given by this number, and then you have to be careful when you expand your calculation precisely just to follow all the signs. There are different sign conventions. This is the one I follow. So the maps, degree 2 minus I, fields, your elements are sitting in the graded vector space with degree k, and this is the homotopy relation. Just know that all my integers here include 0. They start from 0. Okay, this is actually infinite number of relation, and I want to show you just first few of them. So if you start from this n, we start from 0, 1, and then expand possibly relation. So in the lowest order, I just have that map mu1 acting of map mu0 is 0. In the second order, I have mu1 square will give me some map mu2 with this 0 element and my element of algebra. And this is how this relation between these maps look like when expanded. The familiar example you might have in mind is when you set this mu0 element to 0, then this expression doesn't exist. You have mu1 square to 0 because mu0 doesn't exist. So you in this case, map mu1 would be something like it would be a differential. Then the next identity here, this would be 0. So basically, you would have just Leibniz rule for the bracket. Actually, mu2 would be then a bracket, and this would be the Leibniz rule of differential acting on this bracket. So the standard, let's say, graded Lie algebra would have only map mu2. Okay, so this is more familiar, and the only thing to notice, of course, when this mu is 0, so I do have this differential here. There is underlined in my notation cochain complex because map mu1 has degree 1 for me, 2 minus I. And yes, as I said, the standard example is graded Lie algebra with map mu2 just being graded Lie bracket, and maybe one non-standard example, but also very simple. It's a curved differential graded Lie algebra. You have just 3 maps: map mu0, map mu1, and map mu2. So it's a graded Lie algebra. You have the derivation d that doesn't square to 0. You have curvature element of degree 2 such that these expressions are satisfied, and of course you have a bracket. And in L infinity language, you have just a graded vector space L where this curvature element will be your map mu0. This derivation d would be map mu1, which doesn't square to 0, and then you have also map mu t, which is graded Lie bracket, and these are the homotopy relations satisfied by this algebra. So you can define in a just extended the standard definition of Morer-Cartan elements. You can define generalized Morer-Cartan elements in the L infinity algebra setting. So these are the elements of homogeneous subspace with the degree 1, satisfying this generalized Morer-Cartan equation. So in the standard case of the differential Lie algebra, you would have only this mu1 of x plus 1 over 2 mu2 of xx being 0, being equation for Morer-Cartan elements. And this is just generalization in this setting. These elements are of interest because if you can solve this and find the element x in L1 such that this is 0, then you can define new L infinity algebra in which you can actually eliminate this mu0 map by redefining your mu1 differential. in this way, and then you're back in the standard, more standard picture when you have really code-chain complex underlying your L-infinity algebra. But the condition for this is, of course, that in your space of fields, in your tensor algebra, you have these elements that solves generalized Morer-Catan equation. And this is just to show you in this simple example of curved differential graded Lie algebra that if you can solve this equation, you can redefine for x of degree 1, you can redefine your mu1 differential in such a way that it does squares to 0. Okay, but Lie infinity algebra has also nice coalgebra formulation. It has this dual picture, and in this picture, L-infinity algebra is actually a coalgebra over a symmetric tensor algebra with a coderivation of degree 1 satisfying this Kolarnitz property, so it's compatible with the coproduct of symmetric tensor algebra here, such that this differential squares to 0. Having differential squaring to 0, it's being more clear how this relation with BV and U manifold sort of picture come into play. In particular, as we are in the symmetric, graded symmetric setting here, this is the tensor product, which is graded symmetric, and the coproduct that was defined a long time ago by Lada and Markel is given on this form, again, sum over shuffles, just to stress that we start from 0 here, so we will have this 0 element included all the time. And here now you can define you can also define the coderivation, which is important for definition of L-infinity algebra, with graded multilinear maps Bi of degree 1, and they act on full tensor algebra in the following form. And now you can sort of define L-infinity algebra in this setting as a Z-graded vector space with multilinear graded symmetric maps Bi of degree 1, such that the coderivation D is nilpotent. This is just a handy way of writing this expression, just to show that basically this shuffling of the elements here can be understood as a map that does the transposition of the elements and includes the signs of transposition. How do we get homotopy relation in this formulation? So we said we have coderivation that squares to 0. So let's apply the coderivation on a just symmetric product of two elements. You just use the formula I gave you here and the coproduct rule, obviously. And then after some small calculation on the two elements, you get these three relations. So map B1 of B on B0 is 0, map B2 on B0 plus B1 square is 0, and this one for these three elements. And these really do look like the maps in L-infinity I show you here. So this would be like these first three maps I gave you here, mu1, mu2, and indeed there is very definite relation between these maps and the maps I gave you here, and they go by the name, they are maps S, and they go under the name of shift isomorphism, suspension, the isomorphism, different authors call it different. It just, so you have to make a connection with the free algebra picture, you need to shift degree of the maps, because here the maps have degree 1, all of them, and the previous in algebra picture they have degree 2 minus I. So you have to do the shift of degree of the maps, and also degree, you have to shift your spaces by 1. But that's, one just have to be careful of the signs. Okay, and now what it up to now I try to show you. So I show you Hopf algebra with its coalgebra V algebra structure, and then I show you also this co-algebra structure of L-infinity algebra. And now I would like to claim that curved L-infinity algebra is a co-algebra with a co-derivation such that the Colabnitz rule is satisfied and the co-derivation squares to 0. I'm claiming that this structure naturally inherits the structure of the Hopf algebra because we are on the symmetric vector space, tensor space, and with some additional consistent compatibility relation of the antipode bit co-derivation, because we sort of took Hopf algebra and added this co-derivation element. It has to satisfy this relation. And luckily for me, Peter Schrupp was doing something like this in his PhD thesis back in '93. So he was constructing the differential calculus in the Hopf algebra. And now the question is, why is this useful? I'm not sure yet. I just like the observation. For me, it was useful because I could understand a little bit how this braided L-infinity algebra that Maria Dimitrievich et al. Constructed comes about from this side. Because in their construction, they were using the category theory of symmetric monoidal categories stuff. And here we can just use the Drinfeld twist to twist L-infinity algebra. And how this goes? Well, this is my Hopf algebra. This L-infinity here stands basically for the tensor, my vector spaces. It has a symmetric product. It has a co-product, antipode, and a co-unit. I can twist it by invertible twist element F in the double copy of this symmetric tensor algebra, satisfying this relation. And this will give me twisted L-infinity algebra, where this new space, my space of my tensor algebra, is actually the same as untwisted one as a vector space. The coproduct changes in this way, and for the sake of this presentation, I'm assuming that twist is abelian, so antipode and co-unit don't change. I can also now interpret my L-infinity Hopf algebra as a module on which this twisted one acts, and define an L-infinity action on L-infinity algebra as curved L-infinity morphism. This was actually done by Mehta and Zabon when they defined L-infinity action on L-infinity algebra on differential graded algebra as a curved L-infinity morphism. And this, when you apply it, results in something which I called star twisted, which is known with the star twisted L-infinity algebra that has the vector space is the same as an untwisted one. It has star product here now. It has a new coproduct given here on the element of the vector spaces, and the antipodes change accordingly. In my presentation, these are elements of the twist, and these are the R matrices that arise from this twist. Here I'm just taking into account, I'm just considering basically a abelian twist when this R matrix is triangular, so I really have another Hopf algebra. It's not braided, it just becomes another Hopf algebra. And then we know from the old work, people in this room, Paolo was working on this, probably Bragno, Peter also, that these two twisted L-infinity, two Hopf algebra are actually isomorphic. And this was nicely proven in Alex Schenkel thesis in 2001. From the L-infinity picture, this isomorphism actually comes from L-infinity morphisms. So I know that there is a relation between coproduct and co-derivation based on L-infinity morphism. In this case, it would be really isomorphism because the first element of the map would be invertible. And this gives me really sort of understanding of this deformation of L-infinity algebra to braided L-infinity algebra, which they define in a proper categorical language, I understand it as a twisting of L-infinity underlying Hopf structure, and it does give me the deformed co-differential maps. These are the maps that define my co-differential in L-infinity structure. They introduce this star product here. As I said, this algebra has a deformed star. It has a star product here, and then there is a braiding controlled by this map sigma that shuffles my entries in the maps, and this is controlled by this R matrix coming from the twist. And your maps here are given by these maps have to be now braided, graded, symmetric. It means that every time you exchange two elements, the R matrix will appear here. And now you just define the co-derivation with these maps. You do have this condition that basically reproduces your deformed homotopy relation. All I want to say that formal form of homotopy relation is the same, just because we can nicely compose this shuffle from outside, and all the braiding is controlled here. So the formal look of the homotopy relation is the same. It's just when you have acting it really on the elements inside, these R matrices will appear. And just to conclude, this was just one example of why this construction and this observation might be interesting. For me, I want to understand it better in the applying L-infinity in the field theory context. Here, I was just talking about algebras in this talk, but you can encode your whole field theory in L-infinity language. Your fields, your gauge and global symmetries, actually, your equation of motion, all of these can be encoded in L-infinity language. So it's a sort of nice way to systematically describe your theories. What is important is that's why I show you this Morer-Cartan equation. In this setting of the field theory, you think of them as equation of motion. The dual of the co-differential actually can be seen to be related to BRST operator when acting on the fields, dual fields. And in the field theory context, these quasi-isomorphisms of L-infinity algebra are quite nice because they are shown to connect equivalent physical theories. So when you're doing a field definition, when you are integrating out extra fields, you're always using L-infinity quasi-isomorphism to get to physically equivalent theories. So in this context of application non-commutative and possibly non-associative field theories, I'm kind of curious what would be the BV quantization in this respect with this braided L-infinity and Hopf algebras. And there is some initial work of Peter Chopin, BV formalism for quantum group, again, long time ago in his PhD thesis. And there is some recent discussion of Hans, Alex, and Richard of this in the context of braided L-infinity. And I'm related to this point of L-infinity quasi-morphism. One of the crucial things to make this relation between Hopf and L-infinity was to include the zero element in L-infinity algebra, so that I have unitile algebra that is Hopf actually. I need this unit. But then I have this problem that underlying, I don't have this underlying cochain anymore under my curved L-infinity, so I'm not really sure how to do this homotopy transfer for a curved L-infinity algebra. Because for the flat one, there was a nice recent work by Alex and collaborators, how you can do it nicely in this sort of flat L-infinity picture. And I think that mathematics behind this for the curved one also exists. It's just my current ignorance. So I want to look this up. Thank you.
Thank you very much. We have little time for short questions, if there are any. I don't see any questions online either. So let's thank Larisa again. And we continue with Jan Vysoky, who will introduce us to graded manifolds.
Okay, so good afternoon, everyone. I would like first thank to the organizers for inviting me to this lovely workshop. And I would like to tell you about what I mean by Z-graded manifolds. So in a nutshell, Z-graded manifolds is a suitable mathematical theory of some generalized manifolds where functions locally depend on Z-graded variables which do commute accordingly to this Z-grading. Sorry, I just did something. I pushed this button accidentally. Okay, thank you. Yeah, sure. Okay, so this was of course considered in the literature before. So there are two basic approaches to this problem. So for example, people considered supermanifolds with an additional Z-grading like Kontsevich, Shevera, Ruitenberg, Voronov. And there is also another approach to define Z-graded manifolds. Henceforth, I will just call them graded manifolds. Then there is no underlying submanifold. And this was first done, I believe, by Mechta, also by Kataneoshet, and notably by Maxime Perron in his master thesis. And so what will be the optimal scenario to kind of do it like Berezin and Constant and Leitz did it for supermanifolds, but we would like in particular to have Z-graded manifolds where all these graded coordinates have all degrees, not just positive degrees. So this is called N manifolds. And disclaimer, there are some problems with this, right? And I will now try to describe you first the problems. So what is kind of naive approach to graded manifolds? How would you do this? So you start with a graded vector space with finite dimensional graded vector space with zero trivial. This should be K0. K0 is 0. And then you take a symmetric algebra of this graded vector space. So you take tensor algebra and quotient out by the ideal generated by this set. And you obtain a graded commutative associative algebra. And then consider for each U subset of Rn, you consider the algebra in this form. So you tensor the symmetric algebra by smooth functions on Rn on the open set U. And you obtain graded commutative associative algebra for each U. How does this algebra look like? So if you choose homogeneous basis for your graded vector space, then this algebra is precisely the algebra of polynomials in this basis with coefficients in smooth functions on U, such that this coordinates psi, this element of the symmetric algebra commute according to what you want. In fact, you can invent a way how to restrict such functions. So, for example, take open subset of U, and you restrict function in here to the function in here. Restriction is easy. You simply restrict the coefficients. All of the coefficients you restrict to functions on V, and you, in fact, in this way, obtain a presheaf on this Rn on topological space valued in graded commutative associative algebras. And we would like this presheaf to become a local model for graded manifolds. So locally, functions on graded manifolds would be precisely of this form. And issues start to appear. First of all, the gluing property for this presheaf fails. And here is trivial counterexample. So you take graded vector space, which contains just two copies of R. One is of degree -2, one is of degree 2. So you have two basis elements. One is of degree -2 and one is of degree 2. And then you take open subset of R, which consists of disjoint union of these open intervals. And on each of this interval, you define the function fj, which is just this power of psi1 to j and psi2 to j. And this doesn't truncate because psi1, psi2 are even variables. So for every j, this is non-trivial. And you can easily see that there is no function which restricts back to these fj's on U. And the problem is that the only function you could cook up would be infinite sum, but you are in symmetric algebra, you have only finite polynomials in your side. So the problem is that this is not a sheaf. This can be somehow resolved if your graded vector space K is only non-negatively graded. So all the degrees for J less than or equal to 0 are trivial. And these are called n-graded manifolds. In fact, you can solve this by only requiring the gluing property by considering just functions of the same degree. So you only assume that you have some local functions of the same degree, all of them, and then you can glue them together. But if this is not true, this doesn't help. The other issue is that you cannot calculate pullbacks of functions. And here's another example. So you take the same sheaf as above, pre-sheaf as above, and you take some ordinary function. There's some typo, C infinity R over R, something like that. So you take ordinary function, and you kind of would like to calculate what happens if you change variable x to x plus psi1, psi2, which is allowed because psi1 is the degree -2, this is of degree 2, so this is of degree 0, and you leave psi's b. And then you would like to calculate what happens, you have to define what is f when you plug in this coordinate change inside of it. And the way how people do it in supergeometry is they do it using kind of Taylor expansion. You Taylor expand your f, and then multiply it by psi1, psi2 to the power of n, which works in supergeometry because this is finite polynomial, right? Because this truncates, because this become these are odd variables, it truncates immediately, in fact. But if psi1, psi2 have degree 2, this doesn't happen. So this is in fact infinite sum, or so you don't end up back in your algebra, which is bad. So for n-graded, however, this is not a problem because this kind of transformation is prohibited. So this never happen. And there is third issue, kind of technical one, that stalks of this sheaf. I want to define stalks, but stalks of sheaf are not local rings. Therefore, this pair, this topological space together with this pre-sheaf is not local ring space. So the stalks are not local rings, and this is a big problem for morphisms. So this is really important if you want to have some nice notion of morphism. You have to have local ring space. And this also shows that, of course, you can say that I will solve the issue 1 by sheafificating my sheaf, pre-sheaf, and I will be fine. But sheafification doesn't solve problems with stalks. So sheafification is not the way to go. Phyron, in his master thesis, proposed to take instead the algebra when you tensor smooth functions on Rn by formal power series in this size. In fact, the problem is that correctly, this is not, he said that this is the algebra of formal power series in psi with coefficients in functions. That's not true. You have to consider this space. So instead, you have to consider this kind of algebra. This is a space of formal power series in size with values with coefficients in smooth functions on on U. However, there is some subtle issue, which not many people notice, that this is not a graded vector space, meaning that this is not a direct sum of homogeneous subspaces of subspaces of elements of degree J. it's instead a direct product, so you have to consider infinite combinations, not just finite combinations. And the way how to treat this problem is kind of subtly change what you mean by graded space. It's just a technical, thought. So instead of considering graded spaces to be sums of subspaces, you consider just sequences graded by integers. And therefore, the disadvantage is that you don't have any inhomogeneous elements in your formalism. But it usually doesn't matter, because usually when you define everything in graded world, you usually just use homogeneous elements. Morphisms become, instead of just single map from K to somewhere, it becomes a sequence where these maps map from these components to some components of other graded objects. So this is just an example, for example, of a map which shifts degree by L. And you can use this kind of change of wording to define all your favorite categories. So you can have category of graded vector spaces, graded commutative associative algebras, graded rings, graded sets, whatever you want. So it's just a really technical idea. And so now let me tell what is actually the correct local model for graded manifold. So you start with a sequence of integers, non-negative integers, which sums to finite numbers. So this is what I call finite dimensional graded manifolds. This sum has to be finite. And I consider this graded vector space, which is very easy. It's just a graded vector space such that its zeroth component is trivial, and its ith component of elements of degree I is just a r to the power of ni. So this is a very simple graded vector space. N star is just a sum of all the non-zero integers nj. And then you can, of course, because it's just a bunch of Rn's, there is a standard basis for this graded vector space. So you basically collect the standard basis from all of the components and you mesh them together to a single combination of vectors. So this is n star tuple of vectors, and each of them has some degree depending on which part of this graded vector space it comes from. And then you consider this kind of graded commutative associative algebra. So I define the kth component of this graded commutative associative algebra like this. I say that f is a function here. If it can be written as this formal power series, where the sum here is over some set, and it will become clear why I sum over this set. It's a set of n star tuples which satisfy some constraint. These fp's for each p from this set are just smooth function only u subset of r and 0 for each of these multi-indices. And this psi to the power of p is just a shorthand notation for I just take power of psi1 to the power of p1 and psi n star to power of p n star, blah, 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 and I multiply them. And this set is precisely defined so that this has a degree k, right? This is this condition here. And this condition here ensures that this is non-zero, right? Because if you have odd degree, then of course higher power than 0 or 1 is 0. So this condition is there just to ensure that these are not 0, and therefore this is a unique decomposition of this element in the degree k function. And then of course you want to make this into graded commutative associative algebra. So you take two functions and you basically define their product as a function of degree k plus L. So it's z-graded algebra as a formal power series defined by this formula, where this coefficient here is basically the product of formal power series. So this is exactly just the product of formal power series. But here there is some sign appearing because you have to reorder these generators to the correct order, and you use the commutation relation. What happens if you interchange xi's to obtain some signs, and everything is so defined, these sets are so defined, then this is always non-zero, and this is just a sign. So this is the way how you define your algebra. And what are the features of this algebra? So this is a graded commutative associative algebra, so that's fine. The restriction morphisms, where you restrict just the coefficients to open subset V of U, makes this assignment into a pre-sheaf on this topological space valued in graded commutative associative algebra. And in fact, now you can show that this is a sheaf. So this is a sheaf. The problem doesn't happen. Its stalks are local graded rings, if you define what is local graded ring, but there is a notion of local graded ring, and this solves the issue number 3. So this is good. Kind of, we are on a good way. And this graded, so you can pair this open subset U with the restriction of this sheaf to U, and you call this graded local ring space a graded domain over U of a given graded dimension. What is a morphism? What is a morphism of two graded domain? It's in fact a morphism of graded local ring spaces. So explicitly, it's a pair of a continuous map of the underlying open subset, and this phi star is a pullback, so it goes the other way around, and you can pull sections of this sheaf back to sections of this sheaf, the sheaf here. So how you say mathematically, you say that this is a sheaf morphism, and you have to push forward one of the sheaves. So this is it's our sheaves over, both are sheaves over V. And there are some additional properties regarding the local ring structures on stalks, but just basically this is what the morphism of domain is. And the good thing is that these morphisms of graded domains have very simple structure. So in fact, if you take morphism of graded domains, this underlying continuous map has to be smooth. So that's one feature. And the whole phi, so both phi underline and both pullback by phi star, is uniquely determined by declaring what is the pullback of coordinate functions. So you take just the coordinate functions on the graded domain here, and you declare what is the pullback of those functions, and this fully and uniquely determines your morphism of graded domains. So this is a nice feature, and this in fact solves issue 2, because you can fully calculate pullbacks of all the functions you have, so no problems happen. What is a graded local chart now? So I'm getting to the definition of graded manifold. So graded local chart, you start with a graded local ring space, and you say that there U phi is a graded local chart for your local ring space of a given graded dimension. If this U is an open subset, so U has to be open subset of M, and the pair, the phi is a pair forming an isomorphism of graded local ring space with some graded domain. What does it mean explicitly? This means that the phi underlying is a homeomorphism of U with some open subset U hat of Rm0, and basically you can pull for every open subset of V hat of U hat. You have an algebra isomorphism from there's some typo here. There should be C infinity NJ. The sheaf of a 4-graded domain to the structure sheaf of this graded local ring space. So there has to be algebra isomorphism for every open subset, and it in fact defines a sheaf morphism, which means that it's compatible with restrictions in both sheaves. So this is basically what this means. And then you can define what is a graded manifold. Now, so graded manifold is a graded local ring space. It's called graded manifold of a given graded dimension if this topological space has not properties, so it's second countable and Hausdorff, and there exists a graded atlas, which means that you can cover your topological space by domains of graded local charts. So you can cover your manifold by graded local charts, and if such an atlas exists, you call it a graded manifold. So first some notes. So you can immediately show that the underlying topological space is ordinary and zero-dimensional manifold, where you just take this same cover and the underlying homeomorphisms of your graded charts, and this makes this underline A into ordinary smooth atlas. So this becomes ordinary and zero-dimensional manifold. And then, of course, you want to have notion of smooth maps, and you have. So you say that phi from n to n, these are two graded manifolds, is a graded smooth map. If it is a morphism of graded local ring spaces, and there is saying what is a morphism of graded local ring spaces, so it's a pair of a continuous map from m to n. And again, for each open subset V of the underlying topological space of this graded manifold, we have graded algebra morphisms the other way around, from the algebra of smooth functions on this graded manifold to here. And again, it has to be compatible with restrictions, and also there are local graded ring structures on the stalks, and this has to be somewhat compatible with this structure. Just some technical thing. And it turns out that this underlying map is automatically smooth. So every graded smooth map is always over an ordinary smooth maps of the underlying manifolds. And in this way, you nicely obtain the category of smooth graded manifolds. So you can compose smooth maps to obtain smooth maps, graded smooth maps. There is identity. The composition is composition, so it's associative, blah, blah, blah. So you get a nicely behaved category of smooth graded manifolds. So now I should give you some examples. So where graded manifolds appear. So of course, every graded domain is by definition a graded manifold. You can view every ordinary manifold as a graded manifold. Every finite dimensional graded vector space is a graded manifold over the zeroth component of a graded vector space. But in this thing, if this graded dimension is xj, then the graded dimension of the manifold is kind of inversed. This is x minus j. J goes over that. All the degree shifted vector bundles you know from for example physics are graded manifolds in this sense. And in fact, all the n-graded manifolds, non-negatively graded manifolds, are of course graded manifolds in this more general sense. Even all supermanifolds are kind of non-canonically graded manifolds, because every supermanifold is always diffeomorphic, super diffeomorphic to the shifted, degree reversed vector bundle. This is called Betrayal's theorem. And in fact, this degree reversed or degree shifted vector bundle is in fact can be viewed as a graded manifold A1, which this is the same as this K here. So degree 1 shifted vector bundle A. So you can ask, okay, so none of these examples are actually, all of them are, except for this one, are actually non-negatively graded. So you can ask, why I'm not just considering n-graded manifolds, right? And there are some nice examples where you have to consider all degrees. And one example is a cotangent bundle of a graded manifold, because if you take a cotangent bundle of a graded manifold, you end up with a graded manifold which has this graded dimension. So, for example, if M is non-negatively graded, then this term is not. And the reason is that the momenta, kind of canonical momenta, have opposite degree to degree of your coordinates. So these are non-negative, these are non-positive, and they both appear together as coordinates on this manifold. This is important because you want to have, you know, degree 0 symplectic structure on star M. So this is the way to go. And also there's another example. If you start by a graded vector space, then you can consider a graded Lie group of general linear automorphisms, whatever that is. But it turns out that unless X is trivially graded, then this is not non-negatively graded, because you can have maps which both raise degree and both lower degree, and they appear together. So this is not non-negatively graded. Okay, I'm almost out of time. 2 minutes. Okay. So just simple examples what can be done. So for example, you can define what are vector fields. It's working as it should. So vector fields are graded derivations of your graded functions. They form a sheaf. Locally, they are generated by coordinate vector fields. So everything still works nicely. So you can work with vector fields as you are used to from, let's say, supergeometry or geometry. You can define graded vector bundles, and you can define them algebraically. So graded vector bundle is a locally freely and finitely generated sheaf of modules over your sheaf of functions, meaning that for each open subset, you actually have a graded vector space, which is a module, graded module over your functions. Restrictions respect this structure, and this is kind of local trivialization. So your manifold has to be covered by trivialization charts, where this makes this algebra, this vector space isomorphic to this C-infinity MV module, and everything is again compatible with restrictions, and this is called vector bundle. So example of a vector bundle is a tangent bundle, which is defined by this sheaf of vector fields, and one can show, this is nice, that to every this algebraic definition of vector bundle actually yields a unique up to diffeomorphism graded manifold together with a smooth map going from E to M to E to M, such that its underlying map is actually makes this E into an ordinary vector bundle. And so some final summary in 30 seconds. So what can be actually done with graded manifolds? One can show that kind of most of nice things from geometry work. For example, inverse function theorem. You have some nice charts for immersions, submersions. You can have forms, Cartan calculus. This is interesting. You can have nicely defined submanifold. You can define inverse images of a submanifold, fiber products of submanifolds, intersections of submanifolds. You have graded Lie groups. You can do whatever you like with graded vector bundles. You can sum them, tensor them, pull back them. And then you have graded analogs of symplectic geometry basically working with no problem. There are some problems which we don't know how to do yet. For example, it's a very complicated question of flows of vector fields, and therefore it's difficult to prove graded Frobenius theorem for distributions. And of course, this is kind of Achilles heel of graded geometry, is that it's kind of difficult to define integration for graded manifolds. And of course, this is just an advertising. This whole talk is just an advertising for the paper I published like in May, called Global Geometry of Graded Manifolds. And in fact, very similar approach to Z-graded manifolds appeared recently in August by Alexei Kotov, Salnikov, which is called, written here, category of Z-graded manifolds. And I would like to thank you for your attention very much.
Thank you very much. We have time for questions.
So thank you for your very nice crash course. I have a question regarding the algebraic category. It seems to me that there is no obstacle to redo this in the more algebraic setting, where you replace the notion of C-infinity with algebraic function and the notion of manifold with the one of schemes. So that is my first question. The second question is that have you looked at the functor of points of these objects? Because they seem quite interesting to me.
The answer to the first question is I don't know, but it should in principle work if you replace the sheaf of smooth functions with some other more convenient sheaf, so analytic functions that should work.
Yes.
So basically the holomorphic functions that should work without any topological graded manifolds. This should work like a charm, except for some inverse function theorems and blah blah blah. And the other question, functor of points, is some part of this whole theory I still don't understand. And of course, there is a quest to do it. Of course, so the functor of points is, everybody will ask about it when you talk about sheaf. So yeah, that's something I have to examine.
Wonderful. Any more questions? I don't see any questions online either. So let's thank Jan again. And we can continue with our third speaker. So our next speaker is Francesco Bonecki, who will tell us about diagonalization of Nien, who is tensor from invariant polynomials.
Okay, so thank you very much to the organizer for this invitation, giving me the opportunity to give this talk. Well, it's about an activity that I'm having since a few years together with these collaborators, Nicola Ciccoli, Gian Q, Marco Tarlini, and Emanuele Viviani. Emanuele Viviani is a PhD student, and the most recent results that I'm presenting today are based on his thesis. Okay, I think that the topic is a little bit outside of the main interest of the conference. So, and since I also had, due to lack of time, cut the part concerning motivations, I think I would like to simply to locate a little bit better than it appears from my talk, my activity. So let me, thank you. So let me say this, in general, we have this world of quantum spaces. And inside here, we will have quantum groups and quantum homogeneous spaces. So this is quantum groups, and this will be quantum homogeneous spaces. So we all know that when we do the classical limit going h bar going to 0, we land into Poisson manifold, and so we will have Poisson Lie groups and Poisson homogeneous spaces. So my motivation, the reason I'm interested in this activity, these integral models, is just to understand how to go back and recover this quantum geometry from the semi-classical underlying geometry of Poisson homogeneous spaces. In particular, I will consider a subset of compact Hermitian symmetric spaces, and the simple example that I will consider will be just the two sphere with a Poisson structure which is called Poisson-Brouillard. Okay, so this is the semi-classical limit of Podle sphere that appear, for instance, in Gianni's talk. Okay, so this is just for giving the motivation. Okay, so this is the plan of the talk. I will try to introduce this Poisson structure on a compact Hermitian symmetric space, but as a part of a more general, not a more general, but richer geometrical structure, which is this PN, which stands for Poisson 9-Hoys, on compact Hermitian symmetric space. This Poisson 9-Hoys geometry is very closely related to integrable models. So we are actually studying integrable models on these spaces. And this is exactly, well, the part that is missing in my talk is exactly how to use these integral models in order to go to quantization. So I will not discuss this, unfortunately, but I will try more to discuss how we understand this model, how we solve this integrable model, and understand how they behave. So what are these models? You take a coadjoint orbit of a compact Lie group. Of course, as a coadjoint orbit, it has the KKS symplectic form, but there is also a second Poisson structure coming from the semi-classical limit of quantum groups, which is that I call Brouillard-Poisson. Okay, this is just a semi-classical limit of quantum homogeneous space. there is an old result by Koronsky and Rubtsov that states that these two structures are compatible. The inverse of the symplectic form and the Bloch-Poisson structures are compatible if the coadjoint orbit is not a general, flag manifold, but it's an Hermitian symmetric space, so compact Hermitian symmetric space. So the consequences of this compatibility are very important, and I try to summarize the main properties. This is exactly what I refer to as a Poisson 9-Hopf geometry. So we can use, we can compose pi with omega. This pi is pi Brouwer-Poisson, of course, in this example. We can compose this pi with omega. We get a 1-1 tensor, so tangent from tangent to tangent, and we can compute the torsion of this tensor, and which is this formula here, and this torsion vanishes as a consequence of the compatibility. So these properties of vanishing torsion is what we refer by saying that this is a Poisson 9-Hopf manifold. Of course, it's not a more general one, but it's not important. So there are many consequences. For instance, we can take omega minus 1 and compose it with the powers of n. Okay, so if j is 1, we get again pi, but then we can go on and we get a full hierarchy, an infinite hierarchy of two tensors which are Poisson structures and are compatible. So all these structures appearing in the hierarchy are compatible. So for what I have to discuss, it's important, this notion of Hamiltonian forms. So what is an Hamiltonian form? An Hamiltonian form is a one form, alpha, that is closed, but also n applied to alpha is closed. Okay? So these Hamiltonian forms have a lot of properties. And for instance, every Poisson structure defines a bracket on one form. So say okay, this bracket with Tj, we can do the bracket between two one forms. This is still a one form. Between two Hamiltonian forms, this is still an Hamiltonian form. And then we can apply, if df is an Hamiltonian form and df is another Hamiltonian form, so we can go on and continue. We start with an Hamiltonian form df, and then we apply k powers of n, and still they are Hamiltonian forms. So since, well, let us suppose that we are on a simply connected manifold, so they are exact. So we have a hierarchy of functions. So these functions are called, this hierarchy is called Lennard hierarchy. Okay, that satisfies these properties. In particular, the functions appearing in the hierarchy commute with respect to all the Poisson structures of the hierarchy. In particular, there is one canonical hierarchy, which is obtained by taking the trace of the power of this tensor n to the k. So this is canonically defined on this geometry, and they form a Lennard hierarchy. I call this the canonical Lennard hierarchy. In particular, these functions commute with respect to all the Poisson structures of the hierarchy. Of course, this is our candidate for integrable model. We don't know anything about the independence. Of course, this is an extra issue. We wanted that this is an integrable model, and we formulated these properties in this way. In general, you can say that distinct eigenvalues of n can be at most 1/2 the dimension of the space. So we assume, we ask that they are max, the number of distinct eigenvalues is maximal, so it's 1/2 the dimension of the space almost everywhere. If this is true, this is of course is a condition of integrability, of the independence of these Hamiltonians. If this is true, then they satisfy this universal equation, which is n d of lambda is equal to L lambda of d lambda. So these eigenvalues lambda must be thought as action variables of this integrable model. Of course, well, this is a technical remark, but it plays an important role in the construction. These eigenvalue functions in general are defined on dense open subset. In our example, they are typically global continuous functions, but not globally smooth functions, and this creates problem. So let me go to my case. Okay, what we want to do is to understand this model that exists on these compact Hermitian symmetric spaces. Okay, so what does it mean understand the model? We want to understand the space of Hamiltonian forms. Possibly, we want to understand what are the eigenvalues of this 9-Hoist tensor. Okay. So I try to explain this part. So what we need to know about this compact Hermitian symmetric space. So let us call K a compact simple Lie algebra, small k. T is a Cartan subalgebra. We fix positive roots, sigma plus. And then this fixes this operator J on the Lie algebra, which I call it as a complex structure. These E alpha are the root vectors. Alpha is a positive root. E alpha is the root vector of that root. J on the root vector is I multiplied by I. J to E minus alpha is minus I, and this is 0 on the Cartan. So I refer it as a complex structure, even it is actually a complex structure on the space of root vectors. It's 0 on the Cartan. So we take a coadjoint orbit of some element rho phi of the Cartan. Phi is living in the Cartan. How it is defined, this rho phi? Okay, we select phi is a root, is a non-compact root. What is a non-compact root? Is a simple root such that every positive root, of course, which is decomposed along simple roots, in the decomposition, the component along phi can be or 1 or 0. They are not roots with 2 phi, 3 phi, and so. So this is a root, particular root, which has this special property. So you have to go to each linking diagrams and see what are the roots that have this property. But you select one, and this one defines a subalgebra that I call K phi, which is done like this. It has a one-dimensional center generated by this element rho phi in the Cartan, plus a semi-simple part. Okay, so K phi, this is the subgroup integrating this subalgebra, and then the coadjoint orbit is just a quotient of K by this K phi. This is a compact Hermitian symmetric space, can be described in this way. In particular, there is one element which justifies the name of symmetric space in the group, which is the exponential phi rho phi. This the square of the adjoint square of this element is 1. Okay. So what we want to do? We know that we are looking for integrable models. These integrable models must be must give Hamiltonian which are commuting for all the Poisson structure which are in the game. In particular, for the first one, which is the symplectic structure, and we have in the very general tools to construct such integrable models and such commuting functions. So the idea is to try to guess what can be the integral model, so constructing by using these models. So this method. So we try to construct some integrable model with respect to the symplectic structure, and then go to check if they commute also with respect to the Poisson structure. So this method that we want to use is a well-known method in symplectic geometry. It's called Phi method. The idea is very, very simple. So it's valid for every Hamiltonian space. Okay, so our coadjoint orbit is an Hamiltonian space, which means there is a moment map that I denote with mu. And then I take two subalgebra, Kj inside Ki inside K. Of course, the subalgebras, the action of the subalgebra is still Hamiltonian, and the moment map is just the composition of the moment map mu, which sends O to K star, with the projection from K star to Ki star, and then I can go on and project from Ki star to Kj star. Okay, so moment map of Kj, which is the Kj is the smaller subalgebra, can be written as Pj composed with mu, or Pji composed mu of the subalgebra Ki, where Pji is the projection from the dual of the bigger subalgebra to the dual of the smaller subalgebra. So what we do? We take an invariant polynomial of Ki, P, an invariant polynomial of Kj, Q, and then we pull back with the moment map to O, and we compute the bracket. Okay? But then we use this fact that mu Kj, the moment map of the smaller subalgebra, can be factored in the moment map of the bigger subalgebra times this P. And then we put here and we get this. So you see that we get the mu, the pullback of the moment map of the bigger subalgebra in both factors. And since the bracket on the coadjoint orbit, sorry, the moment map is a Poisson map between the bracket of the coadjoint orbit and the bracket on the dual the algebra, I can take it out this mu star and compute the bracket on the dual of Ki. Okay, so this bracket on the dual of Ki is what? Is a bracket between P, which is an invariant polynomial, and some function which is pullback of Q. But invariant polynomials are Casimir with respect to this bracket. Okay, so this is 0. Okay, so just with this very simple observation, you see that every invariant polynomial of Ki and Kj will commute once that are pulled back on the coadjoint orbit. So in order to maximize the number of possible commuting Hamiltonians, you choose a chain of subalgebras. As a application of this simple observation, all the invariant polynomials coming from each of these subalgebra will be involutive. Okay. Of course, you have to discuss if your chain produces enough independent Hamiltonians. This is another part of the story that I'm not going to discuss now. But the problem that I want to discuss now is, okay, we have this, once that we choose this chain, let us see what happens with the second Poisson structure that I denoted with pi, which is this Poisson. Of course, now we have to impose a certain condition on our subalgebra. And the first condition that we impose is this. You remember that I have this complex structure, J, and I ask that J leaves Ki, the subalgebras invariant. So J of Ki is Ki. And of course, even in the perpendicular with respect to the Killing form. So this is requirement 1. And then there is requirement 2. Of course, J is a map from K-perp to K-perp. Adjoint action of K is a map from K-perp to K-perp. And you require that this operation commute. Okay? The adjoint action of any element of Ki commute with this complex structure. So only as a consequence of these two conditions, you can prove this. You take every invariant polynomial of Ki, and you apply the 9-Heuss tensor on P of this polynomial, and then you get this formula where you see that this P tilde, so P tilde is P is a polynomial of degree R. P tilde is the corresponding R multilinear functional. Okay, so it has R entries, and that you compute this multilinear functional on the moment map. But then there is this additional term, D of this element A. So what is this element A? An element A is certain function with values in the subalgebra. Okay, it's not very important that we discuss here the definition, but what I want to emphasize is that the property of this formula depends uniquely on this A, so on the properties of the A. For each subalgebra K, we have this AK. So we have to understand, in order to use this formula, what is this, the properties of this A. So this is a, well, let's say a basic formula. Maybe it's not very telling to you, but it's our starting formula that will give us the result. So first of all, we can ask what happens if I take invariant our problem, just a Poisson bracket between Poisson bracket with respect to invariant polynomial. Okay, it's very simple to check that if you take two invariant polynomial of the same subalgebra Ki, they commute with respect to pi. Good. But unfortunately, it's not true if we take with respect to different subalgebras. We take P in Ki and Q in Kj. Okay, and of course this is what we want. So what we are able to do now is to recognize that there is a sufficient condition in such a way that this property is true, that the commutation also with respect to commutation also between polynomials of different subalgebras. This condition is this one. We take this element A that I defined here. It's an element of the subalgebra K. We take the commutator with a moment map, okay, and we ask that they commute. Okay, this is not guaranteed, but it's a sufficient condition. If this is true, in particular, it is through this property that we are looking for, that all the Hamiltonian that we get are in evolution with respect to the second Poisson structure. So how we can construct this? Okay, this I will go very quick. I just try to give a basic idea. Okay, there is some reasonable way of choosing the chains. Okay. Which is the idea is that you take a subalgebra and then you take in that subalgebra a non-compact root. This defines another subalgebra, and you take a non-compact root of that subalgebra, and then you go on. Okay, so this produces chain of subalgebra for all the cases. So it's not a problem to, and it satisfies the hypothesis that we are looking for. But the crucial point that we need also representation. Okay, so what is this representation? We take a representation of the group K. We have a non-compact root phi, and we know that there is automorphism that square to 1, and then it means that the square e to the pi rho phi must be the representation is reducible, so this must be a number. This number is this a to I k phi. And that means that the square root of this automorphism has at most 2 eigenvalues, plus and minus ak phi. This select 2 representation, b plus and b minus. This is true in general. These representations are representation for k phi, but it's not obvious that they are irreducible. In general, they are not irreducible. So we look for representation such that these v plus and v minus are irreducible representation for the subalgebra k phi. Okay, this is not obvious; it's a requirement, and we call this a phi minimal representation. If this representation exists, well, the basic fact is this one. You take the moment map in this representation. Since the moment map is the adjoint of rho phi has only 2 eigenvalues in this representation, the moment map satisfies a quadratic relation. Okay, so this is the property that makes all the constructions that I'm going to discuss work. Okay, this can be iterated for all the subgroups, subalgebras of the chain. I don't want to say this, but it's very important that when you go to the to every step of the chain. We take this element AK, we compute in the corresponding representation, and we find that it's as a consequence of this quadratic relation is a function of the moment magnitude. So in particular, it commutes. A commutes with mu in this representation. So what will we do? We choose a basis of invariant polynomial, just taking the traces in this particular representation that we have for each step. This will give a certain invariant polynomial. We plug in the formula, the general formula I found before, and then you find this very simple formula. So ND of this polynomial of degree R is this AD is a constant, is differential of dp plus d of p of degree R plus 1. So it's a very simple formula. This characterizes the space of Hamiltonian forms, and even allows to compute the eigenvalues in a very close, simple, in a very simple way. So the only point that we have to discuss if this representation that we call phi minimal exists. And it's very simple to see that in the A, B, C, D cases, it always exists, okay? And so in the classical case, it always exists. So we can use it, for instance, the SUN cases on the fundamental, and the SO with respect to SO. So this third case, we have to choose a spin representation, but still it exists. What's the last thing that I want to say is that we didn't expect, but in the exceptional case, these representations do not exist. You can prove that there are not such representation. So all these constructions that we presented, that I presented, doesn't apply. So what we can do, we have a general result that say that the construction works for the first step of the chain. For instance, in the E6 case, the first step of the chain is the first subgroup is SO10 plus SO2. In this case, we can take invariant polynomial, and that's good. But then we don't know how to go on. The same is true for E7. Okay, so I think it's time to conclude. This exceptional case, well, it was a surprise. We really thought that we could apply the same construction, but it's not true. And at the moment, we don't know if this is really, you see, this representation can be seen as a way to produce a suitable basis of invariant polynomials. Maybe simply means that we don't have such a good basis, but the construction works. We have the chain, and this produces everything. But maybe it's a hint that the behavior is really different in the exceptional case. We don't know. This is something that we want to discover. So what are the other things that we would like to do? Well, understand the lift to the symplectic group point. Of course, this I didn't explain, but it's part of the of a needed step to go to this in this quantization direction. Maybe I can say more words to this sometime. And of course, the final goal will be to connect with quantum symmetric spaces, which have been studied in the theory of quantum groups and quantum homogeneous spaces. Stop here. Thank you.
Thank you very much. Questions?
So I did not understand your setting. So K is not a maximal compact, it's any compact, right?
It's a compact.
Just compact.
Compact Lie group. Compact semi-simple.
Semi-simple inside G. Okay. Now, when you choose your positive system, I don't think it's a comment, not a question. I don't think you're allowed to choose whatever you want. You need to choose a positive system that contains a positive system of K. Otherwise, your construction, I don't think it works, right?
No, because if you want everything, let's say the choice of positive roots is a choice that fixes the Poisson structure, okay? Mm-hmm. Because you can take, for instance, if you do it in the complex in the complexification, you have this quasi-triangular quasi-triangular, you have the arithmetics, the standard arithmetics, right? Which is a sum of over positive roots of E alpha wedge E minus alpha. And you can see that these give a solution for the compact real form. Okay, and so this is the solution that you use for define the Poisson structure on K. Okay.
Okay, so your claim is that any positive system you fix will give you
a Poisson structure on K, and then it goes to the quotient.
And the choice of non-compact root, you say I choose a simple non-compact root.
This is what fixes the coadjoint orbit.
Okay.
Because we are interested in probably not on the group, but on the coadjoint orbit.
So,
okay?
So according to this statement, in case of maximal compact, there could be more than one simple non-compact root.
Exactly.
Okay.
This happens, for instance, in SUN. Every simple root is non-compact according to this definition.
Okay.
And this means that you choose one and you will have some Grassmannian. So you will have Grassmannian 1n, 2n, 3n, okay, according to the root that you choose.
General case. Thank you very much.
Wonderful. Thank you. Any more short questions? Paolo, there's a short question from Paolo.
Just would like a comment on quantum symmetric spaces of the E6, E7 type and what the semi-classical limit hints at.
Well, let's say there is literature on quantum symmetric space in general, in particular of the exceptional which are E6 and E7. Okay. And at the moment, well, this literature didn't give us many ideas, right? Because the language is very different. But it's true that they find certain differences. So even the quantum setting, they find certain behavior, some behavior which is different. It's related to this Helgason theorem, which makes these exceptional groups different from the classical groups. And of course, the idea would be, well, to go in that direction, maybe get some ideas how to solve these problems. But at the moment, I don't know much.
Wonderful. So let's thank the speaker again. Oh, sorry, I forgot to check for the online questions, but I don't see any raised hand. So okay. We conclude our morning program with the final talk, which is a short one. Okay, so George Manolakos will tell us about gravity models on covariant for the noncommutative space.
Okay, hello. First of all, I would like to thank the organizers for the opportunity to talk in this meeting. And I will tell you about a gravity model on a covariant noncommutative space. It's based on these two works, and it's a joint work with my collaborators, Manolakos and Panos. So in the beginning, I'm going to very briefly remind you a couple of things about gravity as a gauge theory in 4 dimensions, and how non-commutativity and gauge theories see each other. And eventually, I will show you the model for non-commutative 4-dimensional gravity. Okay, very fast. We know the second-order formulation of GR, dynamical variable, the metric tensor, curvature parameterized by the Riemann tensor. The torsion is the difference of the Lefibovitz connection, which is 0. We have the torsionless condition hold, and the action is the Einstein-Hilbert one, the scalar Ricci. There is an alternative picture, the first-order formulation. Dynamics are governed by the Philbin and the spin connection. Curvature and torsion are given by these two two forms. These are the expressions, and the action is the Palatini action, E wedge G wedge R, and variation gives the Einstein field equation and the torsionless condition. So in order to see an approach of Einstein four-dimensional gravity as a gauge theory, one has to employ the first order formulation of general relativity and start with a gauge theory of the Poincare group ISO 1,3. It's a 10-dimensional non-commutative group. It's the translations in the Lorentz group, and it can be seen with other ways, but it's okay. In total, it has 10 generators, the translations and the Lorentz transformations, and they satisfy these commutation relations. It's the algebra of ISO 1,3. Okay, for the gauging procedure, one has to introduce a gauge vector field for each generator. Therefore, the obvious choice are the 6 fields, the spin connection for the local Lorentz group. And the less obvious choice is to choose 4 quantities that are space-time vector field and the vector extension of SO 1,3. And the appropriate choice are the 4 field binds. Therefore, the gauge connection can be written like this, as an expansion on the generators, and here are the gauge fields, the field bind and the spin connection. This gauge connection transforms in this way, which is actually the covariant derivative acting on epsilon, where epsilon is a gauge transformation parameter, which is also expanded on the generators of the group. And if you combine all this information, then the transformations of the fields are obtained, and I should stress that these gauge transformations are actually equivalent to general coordinate transformations on shell. So the field strength tensor is this one, given by the well-known formula, and can be decomposed on the generators as well, where here with the translations have attached the torsion to form, and here with the Lorentz generators, the curvature to form. Combining again all the expressions we have, we get the component tensor curvatures, which are actually identical to the ones I showed you earlier on the first order formulation. And now for the action, the Palatini action is considered, but it's actually an unmotivated and choice. It's an a posteriori choice, and gives actually the right results, the torsionless condition and field equations. In order to go to a more motivating way to have the dynamics of the GR through this gauge theoretic viewpoint is to get the sitter group instead of Poincare group, SO 1,4. They have the same amount of generators, but they can be written on equal footing. It's a semi-simple group, that's why this is the algebra. This work was actually from Kibble, McDowell, Mansouri, Samsedin during the 70s and 80s. And they considered that they can do a splitting on the indices. Lowercase a is from 1 to 4, and we have the 5th component separately. And every generator of SO 1,4 got redefined like this in terms of the generators of the ISO 1,3 group. Here are the Lorentz generators, here are the translations, which are rescaled in order to match with these components. We see that we have this M, which is inverse length parameter, and accordingly the gauge connection is written like this, and after the splitting one gets this expression where again these components have been redefined in order to match the ones we saw earlier. Okay, last, the same applies for the field strength tensor, which can be written in terms of the curvature to form and the torsion to form I showed you before. And then one can consider in a more natural way an SO 1,4 invariant quadratic action like this, whereas we see here phi A is an internal space vector field which is taken to be frozen, gauge fixed towards this 5th direction, and this non-vanishing value is responsible actually for the symmetry breaking of the de Sitter to the Lorentz group, and the action gets this form, which after some calculations gets this final form, where here we have a Gauss-Bonnet term, where it doesn't contribute to the equations of motion. Here we have the E wedge G wedge R term, it's a Palatini action actually, and we have also an E to the 4th term, which is plays the role of the cosmological constant. Again, solution gives the Einstein field equations. The sitter is solution, and if this m, this parameter goes to 0, the flat solution is recovered. Okay, a similar construction can be considered about the conformal four-dimensional gravity. I will be very quick here. The group parameterizing now is the four-dimensional conformal group. We have 5 more generators than the Poincare group, and following exactly the same procedure, after defining a gauge connection, one can calculate the transformations of the gauge fields, the tensors, and then consider an action, quadratic form again, that is SO2,4 invariant, and not with the introduction of the scalar field, but with the imposition of constraints, the initial symmetry breaks down, giving the Weil action. Okay, now about the non-commutative framework and the gauge theories. Inspiration came from quantization phase space. We had the replacement of conjugate variables with the Hermitian operators, satisfying this Heisenberg relation. And accordingly, in the non-commutative space, to have the quantization, one can replace with the operators satisfying this commutation relation. This theta is an anti-symmetric tensor and defines actually the non-commutativity of the space. 2 cases are very typical: the canonical case where theta is constant, and the Lie-type case where theta is linear with respect to the coordinate operator. The non-commutative framework admits matrix representation, among others, and that's the one we use here, where the derivation is given by this operation through the commutator, and the integration is actually mapped to a trace which acts on the coordinate matrices. So, for the gauge theories in this non-commutative framework, a natural introduction can be done through the introduction of the non-commutative gauge theories with this calligraphic X, which is the covariant non-commutative coordinate. This has to obey a covariant gauge transformation rule. We said it's covariant coordinate, this one, and A mu, this A mu transforms in analogy with a gauge connection like this in order for these covariants to hold. And epsilon is, yes, a gauge parameter. So, after that, one can define a non-commutative covariant field-strength tensor, which, except for this term, which is actually the commutator of the covariant coordinates, which is expected, there is one more term here in order to render this strength tensors covariant. Okay, in general, we have to deal with non-abelian cases. In non-abelian case, we have to figure out where are the fields valued. So let us consider, for example, the commutation relation of 2 elements of the algebra epsilon, comma a. We get this expression, and we see here that in the last term we have the commutator of epsilon and alpha. In ordinary gauge theories, this term vanishes because it's a commutator of functions of x, which commute. So we didn't have to care about the outcome of this anti-commutator. However, here it's not possible to restrict to matrix algebra because this anti-commutator matters, and neither vanishes nor is an algebra element. Therefore, there are 2 options to overpass this difficulty. The one is to consider the universal enveloping algebra and every produced element from here to include it in the algebra. And the second one is to extend the generators and fix the representation so the anti-commutators at some point close. And we employ the second option. Now about the non-commutative space in which we'll build the model. In general, it's a non-trivial task to construct field theories because they break Lorentz invariance, but there's a special class of spaces, the covariant non-commutative spaces, which don't. Such an example is the fuzzy sphere, where coordinates are identified as rescaled as U2 generators. Our previous work was in 3 dimensions was actually based on this space, where we considered R lambda to the third, which is a foliation of this fuzzy sphere. Okay, and now we need the 4-dimensional space. So the most appropriate one was in the literature was this DS, let's say, non-commutative covariant space. We begin from the commutative case, the ordinary, and then we have to find a version, a non-commutative version of it. So it has to, the coordinates have to satisfy this relation with theta AB to be determined. So the analogy to the fuzzy sphere would say that we should identify the coordinates with generators of the SO1,4, which is the isometry group of the space. But theta AB cannot be assigned to generators, therefore covariant breaks. So requiring covariance, use a group. One can use a group with larger symmetry with a minimum extension SO1,5. So the SO1,5 generator satisfies this commutation relation, and after a two-step decomposition, one can go to a local picture and have this algebra about the operators, which are actually the rescaled generators of the initial group. This is the relation that matters most for us. It's the non-commutative relation of the coordinates. So, combining the gauge theory toolbox and the procedure described in the beginning, one can have a gauge theory, a non-commutative gauge theory on the previous space. So, gauging the isometry group of the space, SO1,4, as seen as a subgroup of the SO1,5. As I said before, anticommutators fail to close, so the solution is to enlarge the algebra and fix the representation. So one ends up with a non-commutative gauge theory of SO2,4 times U1. And the generators, the representation was fixed to the 4x4 to the 4-dimensional one. So the representation is given with combinations of gamma matrices, and after that one can actually calculate the commutation relations of the generators to find the algebra explicitly. Also, since we have a finite number of generators, we did it this way, we built it this way to have anticommutators to close, and now we can do our calculations and find our results with the commutation and anticommutation relations. Okay, so one can start with this action. The field equations are satisfied by the non-commutative space. The space I showed you before is a solution of this action, actually. And the gauge fields can be introduced as fluctuations around these coordinates. So the above action, this one, can take this form and this final form, where we have actually defined the covariant coordinate here, from this way to here, and the covariant non-commutative tensor from here to here. And from this step to the final one, we have defined the field strength tensor. Variation gives the field equations of this theory. Okay, now the gauge connection and the field strength can be decomposed on the various generators, on the 16 generators of the theory, like this. And after some calculations, one can find the expressions of these tensors. Also from this decomposition, one can find the transformations of the various gauge fields. Okay, we have more symmetry than we need, therefore we introduce an auxiliary field in order to proceed to a symmetry breaking in a spontaneous way, like the one I showed you in the beginning. We have this scalar field expanded on the generators again, and we build this action, which is actually here the length scale of the theory. This is a scalar field, this is the field strength tensor, this is a Lagrange multiplier, and the introduction of this field induces a symmetry breaking when this auxiliary field is gauge fixed in this direction, and the expression of the broken action is this one. Okay, the constraints that correspond to the above breaking are these ones, where the two component tensors are vanishing, and this leads to these relations. And the residual symmetry is SO1,3 times U1. Okay, last, this is the commutative limit, decoupling the fields that are related solely to the non-commutative regime. Commutators and anti-commutators return to the ordinary form. Derivation and trace the same. And if we also regard these reparameterizations, then we can see that with a similar procedure to the gauge theoretic approach in the beginning of the Einstein gravity, we are led to the same results. That is, we take the Spallatini action with the E wedge E wedge R, with the cosmological constant and the Gauss-Bonnet term, and we recover actually the results I showed you in the beginning, in the commutative limit. Okay, so this was the construction of the non-commutative gauge theory in 4 dimensions. describing the 4D gravity in a regime where coordinates can be considered non-commutative. And in the commutative limit, the theory reduces to the gauge-theoretic approach of the 4D Einstein gravity. And the next step would be the search for a cosmological model in this non-commutative regime. Thank you.
Thank you very much. And we have some time for questions. Harold with a canonical question.
Hi. But first, I would have many comments, but let me make 2 comments here. So first of all, thanks. I appreciate very much these efforts. But sort of one generic comment is that whenever you have a non-commutative gauge theory, which is not maximally supersymmetric, then one cannot quantize it. So it doesn't make sense as a quantum theory because of UVR mixing. But okay, we can leave this aside, just consider it as a classical theory for a moment. Now, then when you consider non-commutative gauge theories, there is always the U1 sector. And there is no way to get rid of it. And as I always emphasize for many years, and George knows it very well, this alone gives you a gravitational sector. So this defines your frame, a metric, and so on and so forth. Moreover, on the covariant spaces, there is even a higher spin tower, which you didn't even touch. But anyway, now on top of this, you introduced new gravitational degrees of freedom through this standard Poincare gauging. So somehow there are now 2 gravitational sectors which will somehow mix, and it's not clear at all to me what this really is. So one would really have to carefully work out equations of motion and how things propagate. So I think this is very complicated.
Okay.
Thank you. Any other comments or questions? I don't know if... Oh, comment on a comment. Wonderful.
I understand your point, Harold, but so these claims for relating to different approaches that a priori can have their own consistency, in the sense that the theory of gravity arising in this, that you are pursuing this, comes from a completely different mechanism than this one.
Yes, but both are present.
Yes, indeed, both are present. So there should be an effort to relate to that. I agree.
I agree. Yes.
Okay, so there is a mutual agreement. That's great. And if there are no more questions or comments here, and I don't see any either online, let's first of all thank George again. Let us also thank all the speakers of this morning's session, because this concludes today's morning session. And since there's no afternoon program, the scientific program follows tomorrow morning